Okay, so as promised, here is just some notes about doing the data analysis for the Conservation of Momentum lab, because it's going to be a little different from some of the previous labs. The data collection itself will work similarly to what we've done before. And in the page that hopefully you linked this video from, it gives information about how you go and take the data. So starting from pasting the data, I'm using Excel this time. And I went ahead and just eliminated the Y column because we're only going to be using data in the X direction. We see the set of numbers that we're going to be using to analyze for these two sleds. So I've chosen magenta for sled 1 and green for sled 2, and I took the position of each of them. This was the right edge of each of the sleds, and I did that for every single frame. So by now, we did this in the Conservation of Energy lab. We then are going to do something with this. So if we come up over here, right, we got a lot going on and we'll talk about this. One of the first steps we normally do is a conversion from our distance units and our time units. So we already know the number of frames per second, and we talked about how we get the overall that overall distance between the inner rubber bands. Again, these numbers could be slightly different from for version 1 for version 2, so you're going to have to do it yourself. But it turns out we can compute the velocities in terms of the video units, as I'll call them, meaning that my position is measured in pixels, my time is measured in frames, so the natural unit for the velocity going to be pixels per frame. And in fact, if we're just interested in finding the mass of the second sled, then we actually don't need to convert. But it's good to do that anyway, just to put these in real units, and we'll see how we can compute the energy. Just as a note, notice that the magenta and the green are sort of alternating, and that can make it sort of annoying if you're trying to do relative references. There's two ways around this. One, you could go and sort of copy each individual cell and move it over so you get two different columns, one for your first slide, one for your second. That's what I did over here, and I'll talk about this one later. You don't necessarily have to do that. Again, if we go into the formulas, as long as we have maintained the same pattern each time, so for example, if I want to find out what is the velocity for just my magenta one, then I just have to make sure I'm going to G7, so that's up here, minus G3, and then again divided by the time interval, and that puts my velocity right there. And then for the green one, I can do something similar where I just sort of skip ahead. This is going to be G8 minus G4 divided by that same time interval. Notice that even though sled 2, this is what I've noted in green, is initially not moving, I still took its position the entire time, and I'm still going to compute its velocity, because that'll give us a little bit of information about how big our errors are going to be. So hopefully by now we've done this a lot in terms of computing velocities. I'm going to compute the velocities for each of these carts. Again, just copy that formula all the way down. Next, when we go and create the graphs, notice that I've put all of this in one single graph, and that's handy just because it sort of sees, we can sort of put everything in one single graph, what's happening. Again, in Excel, all we would have to do is just select all of the data that we want to put in the scatter plot. The first column is automatically going to be our horizontal axis, and then when we go to Insert, go to Charts, and then Scatter Plot, notice this is what we'll get. And then add units and add chart titles, and this is what we get. So your graph should look something like this, in that we have one cart, one sled that's initially not moving, and then we have one that is moving. And notice, even though we have it on an air track that should be approximately frictionless, it's not exactly frictionless. This line has a slight negative slope, indicating that it is slowing down a little bit. Same thing on the other side. This is after the collision. Notice that we have a change in velocity. For V2, the cart kept moving forward, so our velocity is positive. In V1, sled number 1 is going to be moving backwards, so this will become negative. But notice even then, my velocity starts to dip downward. Again, if I look at sled 2, starts off at 0 velocity. During the collision, it goes up to this high value. Notice the collision itself takes place over a very few number of frames. And that's going to be the case when we look at conservation of momentum problems, is that the collision itself happens over a very short period of time. And if you go sort of frame by frame and look at what's happening, they're only in contact for about 4 frames of this video. And so it happens relatively rapidly. Then what we're going to do is, since we do have friction to worry about, we're interested in what's happening to the velocity immediately before the collision and immediately after the collision. So because we know we have friction coming down here, we could, for example, just take a set of data points before the collision. Again, take the same number of data points on either side, compute the average velocity there, and then do the same thing after the collision. Again, make sure that it is the 2 carts have separated, and take the same number of data points on each side. So if we go and do that, I have annotated in here where our collision is going to begin. In this video, it begins at frame 39 and ends by frame 43. So then what I'm going to do is, these were my velocity values. So I'm just going to take an average value. Here I went over 10 frames. So this is 28 to 47 to calculate the average velocity for one of them and the average velocity for the other one. So here our average is 10.9 or about 11. So again, that's sort of in here. Notice that this initial velocity should be 0, and it's in fact very, very small. And so notice, even though it's not stationary, this is still giving us an initial velocity of 0.05. Now, these are the values computed in pixels per frame. If we then want to convert things to meters per second, we have this conversion factor that we found earlier up here. And let me scroll back up here. And that I get by finding my meters per pixel and my frames per second and multiplying them together to form this weird unit of a meter per second per pixel per frame. So I've multiplied my velocity by this. If my velocity is in pixel per frame, ppf, it'll give me my velocity in meters per second. So that's that 0.053. And that's just handy because I don't have to have a lot of new columns of data here. So I take my velocities here. So this is sled 1, sled 2, and the initial values here they are in meters per second. Same thing after the collision. After the collision, I'm going to take 10 data points. So I've selected things from frame 44 to 53 and took that average. And notice again, this sled 1 is down to 3.75, sled 2 is up to 14.7, and that's those values over here. So you can compute the average and then go back to this graph and make sure that you've identified the correct locations. Again, convert those back into meters per second. Now, when we do this data analysis, again, we have a v initial, we have a v final for 1 and 2, and we can use conservation of momentum along with the known value of the mass m1 to then find the value of the mass m2. And the interesting thing is that because we're going to end up dividing by our values of velocity, we don't actually need to convert to meters per second in order to compute what the mass is. So for this particular lab, again, this in version 2, sled 1 was striking a sled that was a slightly lower mass, and so I got 0.115. Again, yours is going to be different. Yours should turn out greater because your sled 2 is going to be greater than the mass of sled 1. Also talked about how this is meant to mimic an elastic collision. So the other thing we can do is compute the kinetic energy, 1/2 mv squared for each of our objects. So this formula up here is just 1/2 of m1 times v1 squared plus m2 v2 squared. Again, so we need to find this mass first before we find our initial kinetic energy, find our final kinetic energy, and then notice that they're not exactly the same. In fact, we have a slight increase in the amount of energy, again, just due to the statistical error in our analysis. But at 0.04 to 0.04 is pretty close. Now, since we are just interested in sort of what's happening over a big interval, we don't even necessarily have to find the velocity at every single point. So that's where this last tab comes in, and I just was doing this to get an idea of what it would look like. What we have here is I've just taken the positions of each of our sleds, sled 1, sled 2, and sort of moved them to the side so I don't have to do that weird alternating thing. And then I just plotted it. So this is telling me my position graphs rather than a velocity graph. Before we had a velocity graph, these are position graphs. Again, sled 2 is initially stationary. It's got a flat horizontal graph until the collision when it starts moving upwards. And again, the velocity after the collision is just the slope here. Sled number 1 is coming in with some velocity to the left because it's got a lower overall pixel value. Again, we have the collision here, and then it goes off at a slightly different slope. So in fact, what we need, all the data we need, is the slope before, slope after for each of these two. And if we do that, then we don't have to compute the velocity. Excel has a built-in function that lets us do that. So again, I'm going to slide down here. Again, our collision lasted from frame 34 to 44. And so to compute the slope, all I have to do is select my Y data, so B2 to B25. That is going to be this chunk of data here. And A2, A25, the slope function just fits a line through that slope, and it gives me a value of velocity of 11.2. Again, going back to our velocity graph, 11.2, that's about where it should be. And notice that the second method does not take into account friction. Essentially, we've just averaged out over that entire interval rather than just a smaller interval. So we can use the slope function for our first cart, slope function for our second cart. Notice our second cart should be initially not moving. And in this case, we actually get our initial velocities being slightly negative, as opposed to in this one, again, scrolling down where we found it was initially slightly positive. Again, it should be stationary, but because of the statistical nature, it's going to be slightly different from 0. Again, use the slope function after. Again, this is over the next range of data. Okay, another thing I wanted to look at, notice that I took data for sled 2, even though it wasn't moving. So in essence, I was putting down a cursor, a data point at the exact same point for many, many frames. And I did that because I wanted to get a sense of the actual size of my distance error. We've been sort of assuming that, well, I can measure it to within a frame or something. And notice that all of my data for sled 2 all hovers between like 669 and 667. And what that means is that as we're putting down data points, this gives a good idea of just how well I can actually, put down a cursor. It actually gives me information about that error. So if we take an average of that, notice the average position, which again should have been stationary. This is what I put down as the cursor, but more importantly, my standard deviation. How much scatter was there? And this gives me a better estimate of my error. And it turns out that this standard deviation of 0.65 is actually less than 1 pixel. In earlier labs, we've been assuming, well, maybe I can go 2 pixels on either side. In fact, our position, our ability, or at least my ability, to put down a data point at a particular place on the sled is actually better than that. I'm still going to assume about a 1 pixel error, just because we really can't measure less than 1 pixel, but it's just interesting to see that if you actually compute this for a stationary object, this is what we get. Okay, I said before that we can use conservation of momentum then to find the mass, and we don't even have to convert to other units. So this is giving me my v final minus v initial. This is the delta v for each of them, and then my mass is just going to be related to my initial mass of 0.235 multiplied by that a certain velocity ratio, which you'll figure out using conservation of momentum. Here we get our mass of 0.123, slightly different from the 0.115, still less, but slightly different, because of the data we took there. Again, when we do the data analysis, the other nice thing is since we're not computing accelerations, our data analysis is pretty straightforward. From the method of adding percents, the fractional error, the delta v over v, is just going to be equal to our fractional error in time plus our fractional error in position. Let me write these as percents just because they're sort of easier to think about. My delta t over t is just equal to, I took my delta t to be 1 frame. We can't certainly get smaller than that, over the length of time we had in frames. So overall, I took data over 48 frames. So that gives me a delta t over t of about 2.08%, which turns out to be the bigger error. My delta x I took to be 1 single pixel. Again, I know that, based upon this analysis, I might be able to fudge this a little bit shorter, down to 0.65. But just to be honest, since I really can't measure things to within 1 pixel, I'm going to call it just 1. So 1 divided by, again, this is my total range of x for both of the carts. This is the total width of the data there, so the maximum and the minimum, and that gave me an error of 0.13. Adding those together gave me an error of about 2%. So in terms of our velocity measurement, and then similarly for our mass measurement, we can only do things to about 2%. As a quick note about kinetic energy, since kinetic energy goes like velocity squared, I would have to double this. So if I'm just measuring the mass, I can measure the mass to 2.22%. But if I'm measuring the kinetic energy, I can only do that to within 4%. Okay, so this is, again, like I said, a little bit different. We're not actually using any trend lines on any of these graphs the way they had done before. The graphs are sort of handy in terms of letting us visualize what's happening. Again, our position graph should look like this. We should clearly see the collision. We should have about the same number of data points before and after. I'm assuming that everyone's going to do things just in terms of velocity. Again, I plotted things in terms of pixels per frame. You can go ahead and do that in meters per second. I'll still be able to understand it. And like I said, the calculation of the mass is not going to depend upon what units you use to the velocity. So hopefully this helps clear things up as to what some of the things we're asking about in the lab. And as always, please let me know if you have any questions. Goodbye.